Chapter 29 Electromagnetic Induction and Faraday's Law. Units of Chapter 29 include induced EMF, Faraday's Law of Induction, Lenz's Law, EMF induced in a moving conductor, electric generators, back EMF and counter torque, eddy currents, transformers and transmission of power. A changing magnetic flux produces an electric field. Applications of induction, sound systems, computer memory, GFCI. Section 1. Induced EMF. Almost 200 years ago, Faraday looked for evidence that a magnetic field would induce an electric current with this apparatus shown below. As you can see, this apparatus is basically a circuit of wires connected to a battery, and the wires are looping around a circle, forming two solenoids, and they have an iron core. With the help of a galvanometer, he could measure the amount of the current induced in the solenoid Y as the changes in the current in solenoid X. He found no evidence when the current was steady, but he did see a current induced when the switch was turned on or off. So as you can see in the cartoon down here, in part A, if the magnet moves up toward the coil and the magnetic flux or the magnetic field is increasing, we will see a current induced in the circuit, and we will see it on the galvanometer. The other scenario we'll see in part B. When the magnet is moved away from the wire, you will see a current will be induced in opposite direction. But if we keep the magnet without any movement at steady distance from the wire, no current will be induced in the circuit. Therefore, a changing magnetic field induces an EMF. Faraday's experiment used a magnetic field that was changing because the current producing it was changing. The previous graphic shows a magnetic field that is changing because the magnet is moving. The induced EMF in a wire loop is proportional to the rate of change of magnetic flux through the loop. We define magnetic flux as phi sub b and is equal to the integral of magnetic field B, vector magnetic field B, dotted with dA, small pieces of area. Unit of magnetic flux is Weber WB, and 1 Weber is equal to 1 Tesla times meter squared. Section 2. Faraday's law of induction, Lenz's law. This drawing shows the variables in the flux equation. Here we have a loop of size L, and the size of the area is A, and we have a vector, capital A, normal to this surface. That is making an angle theta with the lines of magnetic field, which is a uniform and parallel lines throughout this area of interest. So we can imagine either we have a component of the surface vector A along with the direction of the field, or we have a component of the magnetic field normal to the field, B normal, which is taking part in the magnetic flux. The magnetic flux is analogous to the electric flux. It is proportional to the total number of magnetic field lines passing through the loop. As you see here, if the loops are parallel to the magnetic field, or the normal vector to the surface is perpendicular to the lines of the magnetic field, there is no flux. But if the angle between the normal to the surface A with respect to the lines of the magnetic field are 45 degrees, the flux will be B times A times cos 45. And we have the maximum flux where the normal to the surface is along with the lines of the magnetic field and there's no angle between them. Therefore, the cos 0 is the maximum, and the maximum flux will be magnetic field times the surface area A. So the Faraday's law of induction says the EMF induced in a circuit is equal to the rate of change of magnetic flux through the circuit. So EMF equals minus d phi over dt, the derivative of the magnetic flux over dt over time, and it has a negative sign, so it's opposite to the changes in the flux rates. Or for n loops, EMF is equal to minus n times the rates of the changes in flux over time. The minus sign gives the direction of the induced EMF. A current produced by an induced EMF moves in a direction so that the magnetic field it produces tends to restore the changed field. Or an induced EMF is always in a direction that opposes the original change in flux that caused it. We talk about changes in the magnetic field intensity or the magnitude. We can also think of the magnetic flux changes if the area of the loop changes. So here we have a loop of wires in the magnetic field into the page, and by pulling the two sides of the wire we can change the area, and therefore by changing the area the flux will be changed through this wire loop. Therefore a current will be induced in the wire loop. We can imagine also the magnetic flux will change if the angle between the loop and the field changes. So here we have a loop which can be rotated along this axis, and we have maximum flux when the surface is perpendicular to the lines of the magnetic field. As we rotate this, the flux will be decreasing, and we can have some electric current induced in the wire. When we try to solve a problem using a Lenz's law, we have to take these points into account. 1. Determine whether the magnetic flux is increasing, decreasing, or unchanged. 2. The magnetic field due to the induced current points in the opposite direction to the original field if the flux is increasing, in the same direction if it is decreasing, and is 0 if the flux is not changing. 3. Use the right-hand rule to determine the direction of the current. 4. Remember that the external field and the field due to the induced current are different. Okay, as an example, I'll take a look at problem number 12 in the book. A circular wire loop of radius r equals 12 centimeter is in a uniform magnetic field B equals 0.4 Tesla with its plane perpendicular to the direction of the field. If the field magnitude begins to decrease at a rate of 0.01 Tesla per second, at what rate should R be increasing at this instant so that the induced EMF within the loop is 0? So to solve this problem, we should use equation 29-2a to calculate the EMF. That equation says EMF is equal to minus derivative of magnetic flux with respect to time. Now we have to plug in the values for the magnetic flux as, let's put the derivative here. For the magnetic flux, we can say we have a magnetic field B and it's perpendicular to the wire loop of radius r. So we have pi r squared and it's perpendicular, so the cosine of 0 is 1. Because if this is the wire, we have normal to the surface A, and this plane is normal to the lines of the magnetic field. Okay, it's the magnetic field. So the angle between B and A is equal to 0. Therefore, cosine 0 is equal to 1. So now let's take the derivative. So EMF is equal to minus dB over dt times pi r squared minus 2 pi r b dr over dt. We know about the rate of the changes in the magnetic field. Now we want to calculate what is the rate of the changes in the radius of the loop if we want to counteract the effect of the changes in the magnetic field. So we solve it for dr over dt, and that is equal to minus dB over dt r over 2b. Let's plug in the values. Minus 0.01 Tesla per second multiplied by r is 12 centimeter, so it's 0.12 meter, and the magnetic field is 2 times 0.4 Tesla. Therefore, dr over dt becomes 0.0015 meter per second, or 1.5 millimeter per second. All right, now let's take a look at another example. Problem number 18 in the book. A single circular loop of wire is placed inside a long solenoid with its plane perpendicular to the axis of the solenoid. The area of the loop is A1, and that of the solenoid, which has an n turn per unit length, is A2. A current I equals I naught cosine omega t flows in the solenoid turns. As we can see here, the current is changing with time. What is the induced EMF in the small loop? The magnetic field inside the solenoid is given by equation 28-4, and it's given by B is equal to N mu naught I. Also, we use equation 29-2A to calculate the induced EMF. That is minus d phi over dt, and the flux which is causing the EMF is the flux through the small loop, and it's equal to minus A1 dB over dt, but this B is the field of solenoid, and this is equal to minus A1 mu naught N times di over dt. That is the EMF induced in the loop. So let's plug in the values. So the EMF is equal to minus A1 mu naught N, and the derivative of I with respect to t is equal to minus omega I naught sine omega t. Let's put everything together. We have A1 mu naught N omega I naught sine omega t. Section 3. EMF induced in a moving conductor. The figure below shows another way the magnetic flux can change. As we can see here, we have constant magnetic field pointing outward of the page, represented with blue dots inside a circle. And we have a conductor loop formed from a wire bent inside this magnetic field, and a piece of conductor here is moving to the right, and therefore the surface area of the conductor is changing, and that is increasing. So the induced current is in a direction that tends to slow the moving bar, and it will take an external force to keep it moving. So as you can see here, this bar, which was moving, will have induced EMF inside the bar, which caused the charges inside the bar to be separated at some internal electric field due to the electric force induced inside the bar. So we can calculate this induced EMF with the magnitude as shown here, the same equation for the Lenz's law, and it's given by EMF equals the derivative of magnetic flux over time, and it's equal to magnetic field B inside this area of dA over dt. It is equal to B times LV dt over dt, and dt's will cancel out, and we end up with B times L times V as the EMF induced. This equation is valid as long as B, current I, and V velocity are mutually perpendicular. If not, it is true for their perpendicular components. Let's take a look at problem number 26 in the book as an example. If the U-shaped conductor in figure 29-12a, which is shown down here, has a resistivity ρ, whereas that of the moving rod is negligible, derive a formula for the current I as a function of time. Assume the rod starts at the bottom of the U at t equals 0 and moves with uniform speed v in the magnetic field B, which is pointing outward from the page. The cross-sectional area of the rod and all parts of the U is A. So to solve this problem, we'll look at equation 29-3 for the EMF, which is equal to B times L times V. The resistance of the conductor is given by equation 25-3, and it's given as rho L divided by A. The length in this equation is the length of the resistive material, and since the movable rod starts at the bottom of the U at time 0, in a time t we have moved the distance Vt. So we say the current induced is equal to EMF over R. The EMF we have B times L multiplied by V. For R we have rho L A. So B times L times V. In the denominator we have rho for length L. We have 2Vt plus length L over A. You can simplify this as BLV times A divided by rho 2Vt plus L. The factor 2 here is referring to two parts of the wire down here and up here, which are showing resistivity for the induced current. Section 4. Electric generators. A generator is the opposite of a motor. It transforms mechanical energy into electrical energy. This is an AC generator depicted here. The axle is rotated by an external force such as falling water or steam. The brushes are in constant electrical contact with the slip rings. As you can see here, we have a rotation piece, which is called an armature, between two fixed magnets. By constant changing of the magnetic flux inside this loop, which is rotating, we will induce some currents, and the currents can turn on the light bulb. If the loop is rotating with constant angular velocity omega, the induced EMF is sinusoidal. So EMF is equal to minus B times the derivative of cos omega t, which is equal to B times A times omega times sine omega t. For a coil of n loops, we have to multiply this by factor n. The EMF is equal to nBA omega sine omega t, and can be written as epsilon naught times sine omega t. A DC generator is similar, except that it has a split ring commutator instead of split rings. Here down we see two types of DC generators. Part A, we see it with a one split ring commutator, but in part B we see a DC generator with multiple split ring commutators. Alright, let's take a look at problem number 36 from the book as an example. A generator rotates at 85 Hz in a magnetic field of 0.03 Tesla. It has 950 turns and produces an RMS voltage of 150 volts and an RMS current of 60 amp. A asks what is the peak current produced, and B asks what is the area of each turn of the coil. So for part A, the peak current is found from the RMS current. Peak current is the square root 2 multiplied by the RMS current. It's equal to root 2, 60 amp, and that gives us 84.9 amps. Part B asks for the area, and that can be found from equation 29.4. From the relation for EMF, peak is equal to NB omega multiplied by A. That is equal to root 2, the RMS value of the voltage. Solve it for the area as root 2 multiplied by RMS voltage divided by NB omega. Let's plug in the numbers. Root 2 multiplied by 150 volts divided by 950 turns multiplied by 0.03 Tesla, and that is 85 rev per second multiplied by 2 pi radiant per each rev. That gives an area of 0.01394 meters squared, which is almost 1.4 10 to the power minus 2 meters squared. Section 5. Back EMF and counter torque. Eddy currents. An electric motor turns because there is a torque on it due to the current. We would expect the motor to accelerate unless there is some sort of drag torque. The drag torque exists and is due to the induced EMF called a back EMF. A similar effect occurs in a generator. If it is connected to a circuit, current will flow in it and will produce a counter torque. This means the external applied torque must increase to keep the generator turning. Induced currents can flow in bulk material as well as through wires. These are called eddy currents and can dramatically slow a conductor moving into or out of a magnetic field. As an example, let's take a look at problem number 42 in the book. The back EMF in a DC motor is 85 volts when the motor is operating at 1400 RPM. How would you change the motor's magnetic field if you wanted to reduce the back EMF to 75 volts when the motor was running at 2300 RPM? Okay, the magnitude of the back EMF is proportional to both rotation speed and the magnetic field, which is given by equation 29-4. Since the rotation speed and the magnetic field are constant, therefore the term EMF over B omega is constant. We can write it down as EMF1 over B1 omega 1 should be equal to EMF2 B2 omega 2. If we solve it for B2, we have EMF2 over omega 2 multiplied by B1 omega 1 over EMF1. So plug in the values, solve it for B2, we have 75 volts times B1. Omega 1 is 1400 RPM. Omega 2 is 2300 RPM. And EMF1 is 85 volts. And that gives us 0.54 B1. So we have to reduce the magnetic field by 54% of its original value. Section 6. Transformers and transmission of power. A transformer consists of two coils, either interwoven or linked by an iron core. A changing EMF in one induces an EMF in the other. The ratio of the EMFs is equal to the ratio of the number of turns in each coil. So Vs over Vp is equal to Ns over Np. This is a setup transformer. The EMF in the secondary coil is larger than the EMF in the primary. So you can see on the left we have the primary coil with Np turns, and we have a Vp input, and we have a laminated iron core, which is common in both solenoids, and a secondary coil with Ns turns, a wire, and Vs as the output voltage. As the energy must be conserved, in the absence of losses, the ratio of the currents must be the inverse of the ratio of turns. So we have Is over Ip equals Np over Ns. So transformers work only if the current is changing. This is one reason why electricity is transmitted as AC. As we see here, there's a power plant, generates electricity at 12 kilovolts. We have a setup transformer to increase the voltage to 240 kilovolts. And we have the high voltage transmission lines from the power plant, transforms and transmits it to the transformer substations and reduces down the voltage from 2400 to 240 volts or 120 volts using the step-down transformers into our homes. Okay, let's take a look at problem 48 in the book as an example. A model train transformer plugs into 120 volt AC and draws 0.35 ampere while supplying 6.5 amp to the train. What voltage is present across the tracks? And B asks, is the transformer set up step up or step down. So we use equations 29-5 and 29-6 to relate the voltage and current ratios. So the voltage of the secondary over the voltage of the primary equals number of turns for the secondary over number of turns in the primary. And also the secondary current over the primary current is equal to the primary turns over secondary turns. Therefore, we can conclude V of secondary over V of primary is equal to the current in the primary over the current in the secondary. And we can solve it for the secondary voltage, Vp, Ip over Is. Plug in the numbers. Vp is 120 volt, Ip is 0.35 amp, is 6.5 amp. And that gives us 6.5 volts. For part B, which is asking if it's a step up or step down transformer, because the secondary voltage is less than the primary voltage, this is a step down transformer. Section 7. A changing magnetic flux produces an electric field. A changing magnetic flux induces an electric field. This is a generalization of Faraday's law. The electric field will exist regardless of whether there are any conductors around. Mathematically, we say the integral over closed loop of E dotted with dl is equal to minus the derivative of magnetic flux. Section 8. Applications of induction. Sound systems, computer memory, seismograph, GFCI. This microphone shown down here works by induction. The vibrating membrane induces an EMF in the coil. So here we have a magnet that is close to a membrane with a small coil of wire. And as the sound wave hits to the membrane, a current will be induced in the coil and will be sent to the recorder or amplifier. Differently magnetized areas on an audio tape or disc induce signals in the read or write heads. A seismograph has a fixed coil and a magnet hung on a spring, or vice versa. This records the current induced when the earth shakes. So here is a depiction of the seismograph. We have a suspension spring holding the coil, and we have a permanent magnet. As the earth is shaking, we will have induced current inside this coil. A ground fault circuit interpreter, or GFCI, will interpret the current to a circuit that has shorted out in a very short time, preventing electrocution. Circuit breakers are too slow for this application. So here we have a simple electronic circuit connected to a sensing coil and also connected to a solenoid circuit breaker. And the circuit breaker can turn the switch on and off to prevent electrocution. Summary of Chapter 29. Magnetic flux is defined as the integral of B dotted with dA. Changing magnetic flux induces EMF given by minus N multiplied by the changes in magnetic flux. For N loops, we have minus n multiplied by the changes in magnetic flux over time. Induced EMF produces current that opposes original flux change. Changing magnetic field produces an electric field. General form of Faraday's law is given by the integral over the closed loop of E dot dl is equal to minus the derivative of magnetic flux over time. Electric generator changes mechanical energy to electrical energy. Electric motor does the opposite. A transformer changes magnitude of voltage in an AC circuit. Ratio of currents is inverse of ratio of voltages. So secondary voltage over primary voltage ratio is equal to the ratio of secondary over primary rounds. And I secondary over I primary is equal to N primary over N secondary.